In the second half of our discussion of reactions, we're going to talk about redox reactions in particular. A redox reaction is a short for oxidation reduction reactions, and rather than the interconversion or interchange of ions, involve the net transfer of electrons. Electrons are transferred from a substance that gets oxidized or loses electrons to a substance that gets reduced or gains electrons. So a redox reaction is just a shortened term of oxidation reduction, which in turn are fancy terms for the loss of electrons and the gain of electrons respectively. We need to remember that terminology, and there are two ways that we can use mnemonics to help us remember. We can either remember oil rig, or, my personal preference, Leo the Lion says grr. Oil rig. Oxidation is loss. Loss of what? Electrons. Reduction is gain. Rig. Or lose electrons, oxidize. Gain electrons, reduce. Whichever way you prefer to remember it, we need to keep this in mind. In order to keep track of which substances are oxidized, lose electrons, and which substances are reduced, gain electrons, in a chemical reaction, we need to be able to assign oxidation numbers to everything that's involved in a chemical reaction. All of the elements in a chemical reaction can receive an oxidation number. For ionic compounds, the oxidation number is the same as the charge of an ion. And for covalent compounds, non-ionic compounds, the oxidation number is like the charge that an element would get if it were in an ionic compound. In order to assign oxidation numbers, we're always going to use the most electronegative element and give it its preferred oxidation state. We're going to keep in mind that elements from groups 1A and 2A, the alkali metals and the alkaline earth metals, get charges that we have already been able to predict, +1 or +2. Aluminum gets a +3 charge, all as their preferred oxidation states. Lastly, all of the oxidation states, just like all the charges of ions and ionic compounds, sum together to give us the total charge of the compound or ion that we're interested in. Remember that neutral ionic compounds have no net charge, so all of the oxidation numbers for everything in an ionic compound or neutral compound must add up to 0. All of the oxidation numbers for ions must add up to the charge of an ion. So let me do a few examples with you. Take, for instance, zinc chloride, ZnCl2. To assign oxidation numbers, we're going to approach just the same way that we would have assigning charges to ions. We'll use the most electronegative element, in this case chlorine, as a benchmark. Chlorine is a halogen. It prefers to have a -1 charge as an anion. And because there are 2 chlorines, the zinc in this compound must have to have a 2+ charge in order to compensate for the 2 chlorines present. We say that the charges of zinc and of chloride in zinc chloride are the same as the oxidation numbers. These are the oxidation numbers in addition to charges, and for ionic compounds, they really mean the same thing. In a covalent substance like sulfur trioxide, SO3, we can use a similar approach to assign oxidation numbers. Even though this isn't an ionic compound, we can still recognize the most electronegative portion of this compound, oxygen, as getting a preferred charge, or oxidation number. We know based on oxygen's position on the periodic table that it likes to form -2 anions, and it likes to have the oxidation number -2. There are 3 oxygens, and because there are 3 oxygens, there are 6 total negative charges. our single sulfur has to be able to compensate for all 6 total negative charges. So it itself has to have a 6 plus oxidation number. We'll say that the oxidation number of sulfur is 6 plus. Even in more complicated molecules, we can still assign oxidation numbers. In HNO3, for instance, we can still use the most electronegative atom, oxygen, to begin assigning oxidation numbers. Oxygen is 2 minus. We also know that because hydrogen is at the front of this molecule and is in group 1A, that it gets a 1 plus oxidation state or charge. That leaves just nitrogen at the middle. At this point, we have got a 2 minus oxidation state from each oxygen, and there are 3 oxygens, so that's 6 total negative charges. We've got 1 hydrogen with a 1 plus oxidation state. That's 1 total positive charge. So right now we're at 1 positive, 6 negative, 5 total negative charges. The nitrogen here needs to compensate for those 5 total negative charges by being a 5 plus oxidation state, 5 positive charges. Together, 1 positive plus 5 positives, 6 positives, 3 oxygens that are each 2 minus give us 6 negative charges. So that's how we assign oxidation states to everything in HNO3. In ions, the only difference will be that the charges of everything will add up to the overall charge on our ion. So we need to keep in mind that everything in dichromate will have an oxidation number that in sum total add up to 2 minus, or negative 2. Once more, the most electronegative atom in this compound is oxygen. It's got a 2 minus charge. There are 7 oxygens, so all told, there are 14 negative oxidation numbers from all the oxygens combined. There are 2 chromiums, and because there are 2, we know that each one has to contribute just a fraction of the charges that remain. So something times 2 has to add up to a number that, when added to 14, gives us negative 2. Well, we know that 12 positives plus 14 negatives will give us negative 2. So all of our chromiums together have to add up to a 12 plus oxidation state. What times 2 gives us 12? 6. The chromium in this compound must be a 6 plus oxidation state. Take a few moments at this point to assign oxidation numbers to all of the atoms in the remaining compounds, and then come back to this video and I'll show you these results. The oxidation states are Notice that we almost always exclusively write our most electronegative atom last or rightmost in a chemical formula. There are some exceptions. We'll talk about one type in the next few slides. So in the first part of this chapter, we looked at a few examples of categories of reactions. I want to show you now that many of these categories of reactions are actually redox reactions. In a decomposition reaction, where one substance transforms into 2 or more substances, like in the reaction of mercury 2 oxide under the heat of a flame to produce metallic mercury and oxygen gas, a redox reaction occurs. Mercury goes from having a 2 plus oxidation state to having a 0 oxidation state as an element all by itself. The only way for mercury as just Hg to have any numerical oxidation state and have that oxidation state add up to 0 is for itself to be 0. All elements in their free forms have a 0 oxidation state. Oxygen goes from having a -2 oxidation state in the reactants to having a 0 oxidation state as an element all by itself. Even though it's a diatomic molecule, oxygen is still in its elemental form all by itself and has a 0 oxidation state. The only way for two oxygens' oxidation states to add up to 0 is for them to both be 0. We say that mercury must have gained some electrons, whereas oxygen must have lost some electrons. We'll talk a little bit more about this as we move on. In a combination reaction, two or more substances combine to make a single product. Potassium, as a free element all by itself, has a 0 oxidation state. Chlorine, as a diatomic molecular gas, also has a 0 oxidation state because, again, it's in its molecular elemental form. Potassium chloride, on the other hand, has a chlorine with a -1 oxidation state and a potassium with a +1 oxidation state. Potassium has gone up in oxidation number. Chlorine has gone down in oxidation number. Potassium has gotten more positive. Chlorine has gotten more negative. Keep that in mind as we move forward. Lastly, in single displacement reactions, we also find redox. In an example of silver nitrate reacting with copper to form copper 2 nitrate and metallic silver, we see that silver in the compound silver nitrate has a +1 oxidation state, nitrogen a +5, oxygen a -2. Copper as a free element all by itself must have a 0 oxidation state. On the product side, nitrogen and oxygen remain unchanged, but copper has gone to a +2 oxidation state, and silver has become an elemental form with a 0 oxidation state. Silver goes from +1 down to 0, suggesting that it has gained electrons. Copper has gone from 0 up to +2. It's got more positive, suggesting that it has lost electrons. At this point, let's write that down and make sure that we can reconcile it ourselves. So, going up in oxidation state, becoming more positive. Like copper has done here, must be associated with the loss of electrons. Electrons are negatively charged, so if we lose electrons, we must render a substance more positive. And conversely, going down in oxidation state, getting more negative, must mean that we've gotten an excess of electrons. Electrons are negatively charged, and the only way to get more negative would be to gain some electrons. We've already given definitions to these terms. Losing electrons is called oxidizing. Gaining electrons is called reducing. So, anytime that we can identify a substance which has gone up in oxidation state, gets more positive, or whose oxidation state goes up in the air, and up in the air is oxygen because it's gaseous. Up in the air going up in oxidation state means that a substance is undergoing oxidation. In this reaction, copper is undergoing oxidation. And conversely, going down in oxidation state, down to the ground, means you're reducing in size. Down to the ground, or down in oxidation number, means that you must be gaining electrons. You must be reducing. In this reaction, silver is reducing because it is going down in oxidation number. We can use that information to help us think about what substances are oxidized, what substances are reduced in a chemical formula. And then we'll talk about some confusing terminology relating to agents afterwards. To deal with this problem, we're going to write out a balanced chemical reaction and assign oxidation numbers to every component of every compound or substance involved in both the reactants and the products of a chemical reaction. For example, when lead 2 oxide reacts with carbon monoxide gas, it produces the products elemental lead and carbon dioxide gas. This is a balanced reaction, and the first thing we're going to do to this balanced reaction is for every single reactant and product in turn, assign oxidation numbers to every component of each substance. In lead 2 oxide, the most electronegative element is oxygen, and oxygen likes to have a 2- oxidation state. Lead, therefore, must like to have a 2+ oxidation state in this compound. In carbon monoxide, the most electronegative element is oxygen. It prefers 2-. Therefore, the carbon must be 2+ in oxidation state. When lead is all by itself, as a neutral element, it has no oxidation state. The only way to get lead's oxidation number to add up to 0 when there's just one lead is to have lead be 0. All elements in their free states are 0 oxidation state. For oxygen and carbon dioxide, the oxidation number is -2. There are 2 of these oxygens, therefore the carbon must have a 4+ oxidation state here. Notice that lead has gone down in oxidation state. We said on the previous slide that going down in oxidation state, down to the ground, means one has reduced. We say that the element reduced is lead. Meanwhile, carbon has gone up in oxidation state. It's gotten more positive, meaning that it must have lost electrons. And we'll say that the element carbon has been oxidized. It's undergone oxidation. As a result of some historical terminology and nomenclature, and more so just as a way to confuse introductory chemistry students, we also throw around some confusing terminology in chemistry. We talk about agents. And just like an athlete's agent doesn't play the sport, but arranges for that athlete whom he or she represents to play the sport, a reducing agent doesn't actually get reduced. It just facilitates somebody else getting reduced. An oxidizing agent doesn't itself get oxidized. It just facilitates somebody else being oxidized. In order to facilitate somebody else getting reduced or gaining electrons, a reducing agent must lose electrons. In order to facilitate somebody else losing electrons or becoming oxidized, an oxidizing agent must itself gain electrons. The compound, molecule, or substance in which we find the element oxidized is referred to as a reducing agent. And the molecule, compound, or element in which we find the substance reduced is referred to as an oxidizing agent. What we'll say for this reaction is that because the substance PbO as our reactant contains the element reduced, that PbO acts as our oxidizing agent. by virtue of lead in PbO gaining electrons, this substance allows another to be oxidized. And by a similar vein, the substance that contains the element being oxidized we'll call our reducing agent. Carbon monoxide contains the carbon that is oxidized over the course of this chemical transformation. And we'll call carbon monoxide our reducing agent. The carbon in carbon monoxide loses the electrons that the lead in lead oxide gains. By losing electrons, this carbon facilitates somebody else being reduced. By gaining electrons, the lead here facilitated carbon and carbon monoxide losing electrons in the first place. So we have this roundabout, confusing interchange of substances. But if we can identify a substance, an element, reduced, then the compound molecular formula in which it exists is the oxidizing agent. And if we can identify the element oxidized, then the compound molecular formula in which it exists is the reducing agent. We will always exclusively refer to these things as the reactant side of our chemical formula. Let's do a few more examples so you see what I mean. When iron 3 chloride is produced from iron and chlorine gas, we can write down a balanced chemical reaction to represent that process. Iron, Fe, is an element all by itself, a solid metal. It reacts with chlorine gas, whose chemical formula is Cl2. Remember, chlorine exists as a diatomic molecule. These things react to produce iron 3 chloride, whose chemical formula is FeCl3. We'll say that this is a solid material. A balanced chemical reaction for this process would have a coefficient of 2 in front of iron 3 chloride, a coefficient of 2 in front of iron, a coefficient of 3 in front of chlorine. And the reason that I show you this is that even though we can balance a chemical reaction, those coefficients are inconsequential when it comes to assigning oxidation states. So I can largely ignore these things for the purposes of writing out oxidation states. It really doesn't matter what they are, so long as I know what the chemical substances involved in my chemical reaction are. Iron, as an element all by itself, must have a zero oxidation state. Chlorine, in its elemental form, an element all by itself, albeit two of the same element in a molecule, must also have a zero oxidation state. But in a compound, chlorine, being the most electronegative atom in FeCl3, gets a -1 oxidation state. Iron gets a 3+ oxidation state. We'll recognize that iron has gone up in oxidation state, up in the air, suggesting it's been oxidized. Whereas chlorine has gone down in oxidation state, down to the ground, meaning it has been reduced. So next, let us assign the element oxidized, the element reduced, the reducing agent, and the oxidizing agent for this reaction. We've identified that iron is the element oxidized. Iron is oxidized because it gets more positive. It must have lost electrons in order to get more positive over the course of this chemical transformation. It exists in the reactant side of this chemical reaction as just iron, not in a molecule or a compound. The element reduced is chlorine. Chlorine goes down in oxidation number, must have gained more electrons to become more negative. The substance in which chlorine exists on the reactant side of this chemical formula is a molecule. It's just the diatomic molecule chlorine, Cl2. The reducing agent is iron. The oxidizing agent is chlorine, molecular chlorine, Cl2. All right, let's do one final example. Let's analyze the combustion of ethane and oxygen. I don't expect you to know what ethane is. It's a chemical substance with the formula C2H6. It's a gas, G. It reacts with oxygen to combust. Oxygen is a diatomic molecule much like chlorine, with a chemical formula O2. The products of a combustion reaction are always carbon dioxide and water vapor. So this will always be the general form of a combustion reaction. This is a little bit trickier to balance, but we can balance it nonetheless. A balanced chemical formula for this substance ends up looking like this. Coefficient of 2, 7, 4, and 6 balance the reaction overall. But it's not imperative that we have a balanced reaction for the purposes of assigning oxidation numbers. We can look at the most electronegative atom of most compounds to be able to assign oxidation states, except for hydrocarbons, among some other exceptions. Here, if we assigned carbon its preferred oxidation state, first we might erroneously assign it -4. But that would force hydrogen into having a potential oxidation state that it really doesn't want to have. Hydrogen can only have a +1 oxidation state due to its location on the periodic table, unless it's partnered in an ionic compound as an anion. It's not in an anionic form here, so it must have a +1 oxidation state. There are 6 hydrogens, so there are 6 positive oxidation numbers. There are 2 carbons, so each carbon must have a 3- or -3 oxidation state. Oxygen is its elemental form all by itself, therefore it gets a 0 oxidation state. Whereas oxygen and carbon dioxide, the most electronegative element, gets a -2 oxidation state. There are 2 of them, so carbon must have a 4+ oxidation state here. We can assign oxidation states like normal in H2O because they work out appropriately. Hydrogen is +1, oxygen -2. Overall, we find that only carbon and oxygen change oxidation states through the course of this reaction. Carbon goes from being -3 to +4. It has gone up in oxidation number. So carbon must be the element that's oxidized. Oxidation, up in the air. Oxygen, no matter where we look, either to the oxygen in CO2 or to the oxygen in H2O, has gone down in oxidation number. It must have undergone reduction. So oxygen must be the element that's reduced. The reducing agent is the substance that contains the element oxidized. The thing that contains carbon on the reactant side of our reaction is ethane, C2H6. The oxidizing agent is the substance that contained the element being reduced. The substance that contained oxygen was O2. So oxygen acts like the oxidizing agent, and hence the origin of this terminology. In combustion reactions, oxygen always acts as an oxidizing agent. Oxygen gets reduced, facilitating something else to be oxidized.